In today's lesson, we are connecting limits at infinity with horizontal asymptotes. So first, let's look at, horizontal asymptotes. So here's a picture. I've got this dotted line. Here is the horizontal asymptote. And then limits in relation to the horizontal asymptotes is kind of like looking at end behavior. As you approach infinity, that's like your end behavior, what is your y value approaching? So as x values go towards infinity or negative infinity, what do the y values approach? So for this graph, I have this function 2 plus 1 over x. So the limit as x approaches infinity of the function 2 plus 1 over x, as you approach infinity, it will get closer and closer to it. It'll approach that value of 2. And then going the other direction, the limit as x approaches negative infinity of 2 plus 1 over x. So I'm approaching negative infinity. I'm approaching 2 from the other side, but I'm still approaching 2. So now we're going to look at the rules for finding horizontal asymptotes of rational functions. So rational functions, that's kind of when horizontal asymptotes appear. And then rules to look for. So first rule is if there is a higher power in the numerator of a rational function. So that would just look like x to the 4th plus 2 over x squared minus 1, for an example. Well, what I want you to think about is that end behavior. If you're plugging in infinity in for x, what happens? The numerator has a higher power. Therefore, it's going to grow a lot faster in the numerator than in the denominator. So this example, there's actually no horizontal asymptote in this scenario when the degree is higher in the numerator than it is in the denominator. There's no horizontal asymptote. And what that is when you have the limit as x approaches infinity of a function with that description, the limit is infinity. As x approaches infinity, y also approaches infinity. Okay, so here is an example. Let's look at the limit as x approaches infinity of 2x to the 4th minus 8x plus 1 over 8x squared plus 7. So all you have to do is look at the degrees, the highest power. Because 4 is in the numerator and it's bigger than 2, automatically this will equal infinity. Okay, so then the next one, what happens if the higher power is in the denominator? So an example, 7x squared plus 1 over 2x to the 3rd. So in this case, the horizontal asymptote, if you have a higher degree in the denominator than the numerator, so if you plug in infinity, it's going to grow, the denominator is going to grow much faster than the numerator. And when you have a much larger number in the denominator, it will get closer and closer to 0. So in this case, there is a horizontal asymptote at y equals 0. So if you have the limit as x approaches infinity of this type of function, it will be 0. So here is a specific example. The limit as x approaches infinity of x over x to the third minus 1 plus 3. So I actually added in a little something here just to make us think about this for a second. So degree 1, degree 3. So as you approach infinity of this, it will be 0. But then this 3 is actually, it's like shifting the horizontal asymptote up 3. So in this case, it's 0 plus 3, which is just 3. Okay, so then the third rule is when the degree is the same in the numerator and denominator. Okay, so maybe I have 6x squared plus 2x over 3x squared plus 8. So because they have the same degree, 2 and 2, the leading coefficients is where the horizontal asymptote will be. So horizontal asymptote at these leading coefficients. So in this case, the limit as x approaches infinity of this function. So in this case that I just gave you, 6 over 3, which equals 2. And now here is an example. So limit as x approaches infinity. This one, square root of 16x squared plus 7 over 2x minus 3. Okay, so this one doesn't appear to have the same, but if you're looking at just this part of the function, these don't even matter. And then if you take the square root, you're looking at, 4x over 2x. They do have the same degree, and the leading coefficients, 4 divided by 2 is 2. So as you approach infinity, the y values will approach 2. Okay, now we're going to look at trig functions with horizontal asymptotes. So limit as x approaches infinity of some trig functions. So first, let's just look at a basic trig function. Limit as x approaches infinity of cosine x. So this is just kind of a trick question. This cosine x doesn't have a horizontal asymptote. It's oscillating. So as you approach infinity, this does not approach a single value. So this does not exist. So let's look at some trig functions that do. Okay, so limit as x approaches infinity of cosine of 1 over x. Well, picture substituting a really, really large number in for x. So 1 over infinity, or a really large number, that's going to be close to 0. It's going to approach 0. So really all we have to do is, what is cosine of 0? Cosine of 0 is 1, so this equals 1. There'll be a horizontal asymptote at y equals 1. And last example, let's look at similar to this last one. So limit as x approaches infinity of sine x over x. So let's just think about, so sine of really large number over really large number. Well, plugging in a really large number, so sine, plugging in a really large number is either the range, the y values are going to range from, 1 to -1. So, and then on the bottom, so if we just have, let's say, somewhere between, -1 and 1 over a really large number, this will be 0. Okay, so there's your full video looking at horizontal asymptotes and how they relate to limits at infinity. Good luck with your lesson.